Ever wondered what makes water flow? Let's find out together. Welcome to Fluid Mechanics 2, brought to you by CED Engineering Academy. Our guide, the renowned Prof. Dr. Alamgir Khalil from UET Peshawar. Known globally as the king of fluid and hydraulics, he's ready to take you on an educational journey like no other. Join us, master the mechanics, and transform your career. Subscribe now for more.
So, Bismillahirrahmanirrahim. This is lecture number 10, Unsteady Flow Problems. Today we are going to start another chapter. This is chapter number 12 in our textbook, Unsteady Flow Problems. First, the learning objectives for this chapter. So, after completing this chapter, you should be able to understand unsteady flow problems. So far, what we have studied, especially the pipe flow chapter, so you saw that all the problems that we discussed, they were steady flow problems. Even the name of the chapter was Steady Incompressible Flow in Pressure Conduits. So this chapter, we are going to study the unsteady flow problems. Clear? So you will be able to understand what are the unsteady flow problems. Similarly, you should be able to calculate the time for draining or emptying a tank and reservoir. This is also an unsteady flow problem, one type of unsteady flow problems. For example, we have a tank and reservoir and we want to drain it by orifice, like we have a tank, we want to drain it by orifice, or reservoir, we want to drain it by a spillway or where, or how much time it will take for water level to change from one level to another, or you want to completely empty the tank. So this we are going to learn in this chapter. Similarly, to calculate velocity of pressure wave in pipes. So this is very interesting and important topic that we are going to study. When water or any liquid, it is flowing in pipes and the liquid is suddenly brought to rest. For example, we close the valves. So what happens is that we are destroying the momentum of the water because you suddenly bring it to rest. So what will happen that since the energy, kinetic energy is destroyed, so we already learned from law of conservation of energy that energy cannot be created nor destroyed. So what happens that it converts into another form. So when the kinetic energy is destroyed, the pressure is increased. So as a result of this pressure wave setup, and this pressure wave, it will travel back and forth. So these pressure waves, we are interested to calculate the velocity. Clear? That with what velocity these pressure waves, they will travel. And this will give rise to what is known as the water hammer. So water hammer is a phenomena in which these pressures, because of these pressure waves that are developed, and we are interested to calculate the critical closure times for the valves. Because these valves, these are important components of the piping systems. So not only in water supply systems, but for example, in dams, when the water is supplied through tunnels to the powerhouse, to the turbines, so you see huge quantity of water is flowing. So there, if you suddenly stop the water, then you can see that the pressure that is going to be developed, it can burst the pipe. So these are known as water hammer pressures. And we would like to calculate that what are the critical closure times that we need to avoid so as to keep this pressure minimum and avoid any damage. Clear? So very interesting topics that we are going to cover in this chapter. But remember, these topics that we will cover are not the only unsteady flow problems. We have so many other practical cases of unsteady flow problems. But as far as we follow our textbook, so these two types of unsteady flow problems that we are going to discuss and we are going to learn. So after completing this chapter, you should be able to understand and calculate all these phenomena, etc. Clear? Now, before we start, what is the problems that we are going to study in unsteady flow? First, we discuss what is steady and what is unsteady flow. You studied in Fluid Mechanics 1 briefly about this, what is steady flow, what is unsteady flow. Similarly, you studied about compressible fluids, incompressible fluids, clear? When the density is constant, so that is incompressible. When the density varies, it is compressible, and so on. Similarly, you studied about uniform flow, non-uniform flow. In this fluid mechanics too, from the beginning, we talk about laminar flow, turbulent flow. So these are the different types of flows, different flow regimes that we study, clear, in detail. So now in this case, we just want to define that what is steady flow and what is unsteady flow before we start and study unsteady flow type of problems in detail. So this steady flow, what is steady flow? A fluid flow is said to be steady if at any point in flowing fluid, various characteristics such as velocity, pressure, density, etc., which describe the behavior of fluid in motion, do not change with time. So this is steady flow. When the fluid characteristics, for example, we have this velocity, pressure, density, discharge, etc. When these characteristics, when they do not change with time, we say that it is steady flow. Remember, it has to do with the time. If the flow characteristics, if they do not change with time, we say that this is steady flow. So for steady flow, what we can write down is that partial v by partial t equal to 0. What it means? It means that the change in velocity with respect to time, that is 0. It means that velocity is constant. It is not changing with respect to time. So that's why this is steady flow. Similarly, we can write down partial rho by partial t equal to 0, density. Similarly, partial q by partial t equal to 0, discharge. Partial p by partial t equal to 0, the pressure. So for steady flow, the fluid characteristics, they are constant with respect to time. Even a single characteristic is changing, then the flow will be unsteady flow. So in an example, we have so many examples we have studied so far. A lot of cases all were steady flow conditions, but a simple example is that a constant discharge through a pipe. When we have a pipe and the rate of flow is constant, it is not changing with respect to time, means that let's say 8 a.m. we have a discharge of, at this pipe here, the discharge is flowing. So at 8 a.m. the discharge is, let's say for example, 10 cubic meter per second. And then after 1 hour, after 2 hours, it is still 8 cubic meter per second. So it means that the discharge is not changing. It is constant with respect to time. Clear? So there we can classify this type as steady flow condition. So in this case, when the velocity is constant with respect to time, clear, equal to 0, it means that it is not changing, means that v is constant. So this we call as the steady flow. So all the cases that we studied so far, they were dealing with steady flow conditions. Means that, for example, we studied a lot of topics that we covered in the pipe flow chapter especially. So in that case, we never consider any quantity that is variable with respect to time. So a steady flow is one in which all conditions at any point in a stream remain constant with respect to time, but the conditions may be different at different points. What does this mean? It means that, for example, you consider this is now a pipe, or we have, for example, in a natural stream of river, normally you have, so if you take one cross section, let's say xx, clear, so at this point you have a discharge, clear, so this discharge is the same with respect to time, so we have steady flow here. But let's say at any other far point here, clear, and you consider another section, let's say yy, so at this yy, it is possible that the discharge will not be the same as at xx, because there could be a possibility that there is some outflow. There is a possibility there can be some outflow, or there is a possibility, as you already see that in the streams, we have either water adding to the stream or leaving the stream, clear. So it means that the discharge here will be different than here. So it doesn't mean that this is unsteady flow. We just take one section at any point. You see, this definition is from your textbook. This definition is from your textbook. What it says? It says that a steady flow is one in which all conditions that we studied at any point in a stream remain constant with respect to time, but the conditions may be different at different points. So it means that at this one section you take, if the flow characteristics are not changing with respect to time, it is steady flow, but the conditions may be different at different points. So here the discharge may be different than this one due to these factors, inflow or outflow from the side channels. But again, here if you take, the discharge is different, but again, if it is not changing with respect to time, so we will say that it is a steady flow. So this is what we mean by this definition, that the conditions should not change with respect to time at any point, but at any other point the conditions may be different as compared to this point. So this definition is from your textbook. This is what it says, clear? So in simple words, when the flow characteristics at any point in the flow, when they are not changing with respect to time, this is steady flow. Next we take the unsteady flow. So a flow is said to be unsteady if at any point in flowing fluid, any one or all the characteristics such as velocity, pressure, density, etc., which describe the behavior of fluid in motion change with time. So what it says that if you take one section in a pipe flow, in a river, in any channel, and if all the characteristics or anyone, even one of the characteristics is changing with respect to time, then we will say that it is unsteady flow. We will say that this is unsteady flow. So for unsteady flow, we can write down that partial V by partial T is not equal to 0. What it means? It means that velocity is changing. The change in velocity with respect to time is not 0. So it means velocity is not constant. Similarly, partial rho by partial T not equal to 0, partial Q by partial T not equal to 0, partial P by partial T not equal to 0. So all of them, all the characteristics which describe the behavior of fluid in motion, or even any one of them, if that is changing with respect to time, we will say that it is unsteady flow. So remember, you study about compressible and incompressible fluids, uniform flow, non-uniform flow, steady flow, and unsteady flow. So now your question can be that when the flow characteristics are changing and when they are not changing, why we are interested in this? Why we need to study about this? That let's say, for example, if at any point the discharge is constant with respect to time, so we say that it is steady flow. We say that it is steady flow. But if it is changing with respect to time, we say that it is unsteady flow. Why we are interested with this? Clear? The thing is that what you have seen so far, that when we deal the flow as a steady flow and when we deal the flow as unsteady flow, we have different analysis techniques. They are not essentially the same problems. So that's why we need to understand. If we have a laminar flow, just to understand this, you see, we have laminar flow. Now in laminar flow, the analysis is different. What we did, we treat the velocity as in one dimension, and we simplified our mathematical analysis, and it was very good because we can derive the formula very easily. We can understand everything very well. And when we come to turbulent flow, the velocity essentially 3-dimension. The analysis become very complex. And I told you that we do not have 100% accurate model that can explain the turbulent flows. So the thing is that when we are going to study a phenomena, we are civil engineers. We are going to construct structures, hydraulic structures. So they are going to be designed for steady flow as well as unsteady flow conditions. So why we are interested to study these steady and unsteady flow? Because they have separate analysis and design techniques. So that's why when we deal a problem and we treat it as unsteady flow, you will see later on in this lecture that the energy equations, they become different as we write down them in steady flow. When this affects our analysis, and definitely this will have impact on the design. So that's why we are interested to study and differentiate these different types of flows and these different types of flow regimes. Okay, so now the unsteady flow, where the characteristics are changing with respect to time. A simple example can be a variable discharge through a pipe. So if, for example, the flow occurs in a pipe, and let's say at 8 a.m. the discharge is 10 cubic meter per second, and then after 1 hour you again calculate the discharge and it is 15 cubic meter per second. After another hour the discharge becomes 5 cubic meter per second. So it means that the discharge is changing with respect to time. So that is an example of unsteady flow problem. So now that we are going to study unsteady flow problems, so there are two main types of unsteady flow problems that we are going to discuss in this chapter, because we follow the textbook. So two main types of unsteady flow problems we are going to discuss. The first one is that when a water level in a reservoir or a pressure tank is steadily rising or falling, so that the rate of flow varies continuously, but the change takes place slowly. This is one type of problem, main types now. So what is this problem? For example, if I give an example, what we studied, you studied in fluid mechanics, the orifices. Well, let's say we have a tank, and let's say we have this orifice, and from here the water flows out. And this water which is flowing out from this tank through an orifice, the discharge is occurring under this head H. Clear? This is H. And you already studied orifices in detail. For example, the discharge for this orifice, this will be equal to cross-sectional area into square root of 2gh. So this is Q is equal to AV. This 2gh, essentially this is the Torseli's theorem, 2gh. This is what you derived by applying Bernoulli equation. So this is Q is equal to AV. So this is now theoretical discharge. If we calculate the actual discharge due to losses, then we write down here a term which is known as coefficient of discharge, CD. So this is the formula for orifice. Now I'm not going into detail. You studied small orifice, large orifice, types of orifice, square orifice, and so on. We are not going into detail, but just to understand that now in this case, this is the formula. So what is happening? Now the water level in a reservoir or pressure tank is steadily rising or falling. This water can rise, this water can fall. So the rate of flow will change continuously. How? Let us assume there the water level is falling, in this case because of the fluid which comes out. So now you can see that in this equation, what is happening? In this equation, this H is changing. Is it constant? No. Because the water level will go down, there is no inflow. We do not have any inflow. There is no inflow. Let's say Qi. So there is no inflow. This is equal to 0. When there is no inflow and when there is outflow, so then in that case, what is happening? Let's say this is Q naught, the outflow discharge. So this is outflow, the water level will fall. So when the water level fall, the H is changing. So when the H is changing, then the discharge will change. So it becomes the unsteady flow problem. Is the water level, because the discharge is changing with respect to time. So a water level in a reservoir or pressure tank is steadily rising or falling, so that the rate of flow will change continuously. But in this case, the important thing is that change takes place slowly. Because when you drain a swimming pool, for example, this can be a swimming pool, and you want to drain it. So through orifice at the bottom of a swimming pool or whatever, it will drain. But you see that the water level steadily goes down. So that's why the changes that take place, it will take place slowly. One type of unsteady flow problem. The second type of unsteady flow problem is when velocity in a pipeline is changed rapidly. When the velocity in a pipeline, it is changed rapidly by fast closing or opening of a valve. We commonly observe this. How? Because when we suddenly open the valve, as in our houses, in the kitchen or in the washroom, the water rushes through it. You see the change that occurs rapidly. Or the water is flowing in a tap and you suddenly close it. So you suddenly close it. It doesn't take that, okay, when you close the valve, it will take 1 hour for water to stop. No. Although we have different types of valves, the one that can rapidly you close it and the one that you can slowly close it, but still you see that in that case, the changes that take place that are rapid changes that take place. Clear? So these are the two main types of unsteady flow problems. In the first case, the example, water level rising or falling in a tank. So the changes that take place, they are slowly. The change take place slowly. And when we first closing or opening of a valve, so in that case, the changes that take place rapidly. These are the two main types of unsteady flow problems. And in this course, we are going to study both of them in detail. So in the first part, we will cover this we will cover in today's lecture. And inshallah, in the next lecture, we will cover this part. Clear? Now, the point to be noted is that these are not the only unsteady flow problems. Remember, clear? Unsteady flow also includes such topics as oscillations in connected reservoirs and in U-tubes, clear? And such phenomena as tidal motion and flood waves in open channels. These are also unsteady flow problems, but we will not discuss them as per our textbook in this course. For example, the floods which come, you can see that the changes that take place with respect to time. So that is essentially unsteady flow problems. But floods, we are not going to cover in this course. Only these two main types of unsteady flow problems we are going to understand, and we are going to study them in detail. So now we start with the first type of unsteady flow problems. Discharge with varying head. Discharge with varying head. So now, before we try to develop an equation, now in this case, we consider an arbitrary shaped tank. Now in this tank, you can see that there is an inflow. So the inflow to the tank, that is denoted by Qi, means the inflow. And from the tank, we have the outflow. So this is the Q naught. Now in this tank, the liquid is contained. So the level of the liquid, that is denoted by Z. It can be denoted by H. You can denote this by H, as you might have done in case of orifices, notches, where you calculate the discharge. So it was essentially, the head was denoted by H. But in our textbook, this water level, whatever it is denoted by Z. So that's why we will stick to this sign convention that Z will represent the water level in a tank or in a reservoir, and then the change of water level, that is denoted by dz. This Z will be with respect to a datum that we have to select. Similarly, this AS, it denotes the surface area. What is the surface area? That let's say I consider this water level. Let's say this is the water level that I consider, this water level here. So for this is the surface area. This is the surface area. So this is denoted by AS. Now this surface area, you can see that it is not constant. Why? Because if I consider another surface of water or liquid at this point here, then this will be the surface area. So in this case, this surface area is not constant. Clear? Similarly, for volume, we denote this using this notation for volume. This is for volume. This notation we follow because we are using for velocity. So to differentiate this from the velocity notation v, we will denote volume by this. Now this dv, this is change in volume. So the change in volume will be the surface area multiplied by the change in water level. Now you understand that the different notations that we are using representing the different variables. So now we discuss discharge with varying head, because when the head is changing, the discharge will change, as I showed you earlier. So this is essentially an example of unsteady flow problem. When flow occurs under varying head, the rate of discharge will continuously vary. Consider a water tank, which is shown here, with inflow Qi and outflow Q0. Let V is the volume of liquid contained in the tank at a particular instant of time. So let this is the volume of liquid contained in this tank at any particular instant of time. Change in volume during a small interval dt can be expressed as. Now we consider a small interval of time dt. So in this dt, how much change in volume will occur? You can see that volume entering the tank, that is given by Qi into dt. Volume entering the tank, that is denoted by Qi into dt. You can see here how it is the volume, because this Q, it is cubic meter per second. And then this discharge is cubic meter per second and dt is second. So you can see that second and second cancel and we are left with the units of volume. Cubic meter, cubic feet, whatever. So volume entering the tank, it is given by Qi into dt. So Qi is the inflow, that is entering. Qi into dt, that volume has entered into this tank in time dt. So now also we have outflow from this tank. So volume leaving the tank. Now we have volume leaving the tank, that will be equal to Q0 times dt. So this Q0 multiplied by dt, that will be equal to the volume that is leaving the tank. So what will be the change in volume? Difference of the two. What will be the change in volume that can occur? We are not saying the volume is increasing or decreasing. No, we are not saying this. What we say is that what is the change in volume? So the change in volume, that will be equal to volume entering the tank minus volume leaving the tank. Qi dt minus Q0 dt, that will be the change in volume. If AS is the surface area of the volume and dz is the change in level of the surface, then this change in volume is equal to AS into dz. Change in volume is also given by AS into dz, because dz is the differential change that has taken place. So that change in the water level multiplied by the surface area, that is also the change in the volume. Clear? Now that we have equation 1 here, change in volume is given by this, and also we have change in volume which is given by this. So we can compare when the left hand sides of equations 1 and 2, they are equal, the right hand side can be compared. So that's why comparing equation 1 with equation 2. So we get AS into dz is equal to Qi dt minus Q0 dt. Now in this, so for discussion, what we say that either Qi or Q naught or both may be variable. In this case here, since the water level can go up and rise, so definitely commonly Q naught will change because the water level can increase or decrease. Q naught can change. If you want to keep it constant, what you have to do? If you want to have steady flow, that this Q naught does not change with respect to time, what you have to do? Just keep the water level constant. Keep the water level constant. Just like, for example, you might have studied about in geotechnical engineering lab also. So there we can keep the water level constant and variable in order to calculate hydraulic conductivity, etc. There you know better. So if I want to keep the head as constant, then you have to supply a constant water supply here. So the head can be maintained, and we can have an outflow that can also be constant because the head is maintained as same. So what we are saying is that either Qi or Q naught or both may be variable. But commonly what we see is that Q naught, that is variable, and Qi, it can be zero, it can be constant, it can be variable. So as I said that Q naught is usually a function of Z. For example, if a liquid is discharged through an orifice or a pipe of area A under a differential head Z, then in that case we can write down this equation. So CD is a numerical discharge coefficient and Z is variable. So Q naught is variable. When Z is changing, the water level is changing, so it will change the discharge. So Q naught is usually a function of Z, so it is variable. If liquid flows over a weir or spillway of what thing I should repeat?
आपने कहा ना कि हम हेड को कांस्टेंट करते हैं, उसके बाद की समझ नहीं आई फिर.
So if you keep the head constant, if Z is constant, what will be the discharge outflow? This will also be constant, correct? So in that case, Qi will be not variable. But let's say when we have a tank in more reservoir, then in that case, if let's say Qi is 0, let us assume Qi as 0, then what will happen? And you have Q naught. What will happen to Z? Z will decrease. Unless and until that this tank is completely emptied. So then in that case, Q naught, it is variable. Understand? Z is changing, Q naught is variable. But I said that if you want to keep the Z constant, how you can do it? The outflow has occurred, there is an outflow, and this outflow is a function of this Z. If you want to keep this Q naught as constant, what you have to do? You have to supply the water so that the incoming discharge is equal to the outgoing discharge. Then in that case, what will happen? This Z will be constant. Is it clear right now? Next, let's say, for example, if we have a weir or spillway, then in that case, this is the equation that you have studied in flow measurement chapter in fluid mechanics 1. So Q naught is equal to CL into H3/2 for a weir or spillway. Now here we are not discussing the notches, etc. that you studied, triangular notch, rectangular notch, trapezoidal notch, and you have specific formulas for that. No. We are in general term discussing. If we have a weir, we can write down the discharge equation for outflow over the weir. That can be CL into H3/2. L is length of the weir, H is the head of water over the weir or spillway, and C is the appropriate coefficient to calculate the actual discharge. Clear? So what we are saying here is that in this equation, that the inflow and the outflow discharge that appear, we are discussing that they can be treated as constant or variable. So what is happening is that because Q naught, it is usually a function of a Z, so Z is variable, then Q naught is variable. Clear? We can see from this formula. This is for the outflow. So commonly, the cases that we study, Q naught is variable. Function of Z or H, they are variable. So Q naught commonly varies with time. We consider only the cases where Qi, the inflow discharge, is 0 or constant. Here, this Qi, we will consider either equal to 0, means there is no inflow, or it is constant, means any constant discharge is coming to the tank, whatever the value. Any constant value is coming, means 10 cubic meter per second, 1 cubic meter per second, whatever is the value. But it is coming with a constant value. Now the question is that this, what is given here, that we consider only the cases where either Qi is 0 or Qi is equal to constant. So as per our textbook, the problems that we are going to solve, Qi will be either 0 or it will have a constant value. Now in our textbook, we will not consider a case where the inflow discharge is variable. This is written in your textbook. But it does not mean that Qi is not variable. Qi can be variable. This Qi, inflow rate, it can be variable. It can also change. It can be variable. But this case is not discussed in our textbook. If you are interested to discuss a case where the inflow discharge is also variable, you can study a book, for example, Hydraulics and Fluid Mechanics by E.H. Leavitt. Hydraulics and Fluid Mechanics by E.H. Leavitt, which is a British book, and it is available, a hard copy available in our library in the civil engineering department. You can study that book and you will find they discuss a case where inflow discharge is treated as variable. And you will see that very complex equation we will get. But anyhow, in our textbook, we will assume that Qi is either equal to 0 or it is constant. We will not consider a case where Qi is variable. So now we come back to this equation. Now we are clear about all the terms. This is the change in water level. This is the surface area, no problem. This is the time dt. And now we are clear about Qi and Q naught. So what we can do is that we can write down dt equal to as dz divided by Qi minus Q naught. So now we can integrate this equation. Just simply integrating this equation gives an expression for time, the time for water level to change from Z1 to Z2. When you integrate this equation, so we integrate from 0 to t. Now you already know that integral and derivative, they are opposite. So they cancel out. And the right hand side from Z1 to Z2. So that's why we are left with t. And now if we want to calculate the time, clear, this right side of equation 4 can be integrated if Qi is 0 or constant, and if as and Q naught can be expressed as a function of z. So we can evaluate this integral to calculate the time, how much time it will take. What we are essentially saying that let's say this is level 1. This is the level 1, and this level here, this is Z1. This is your Z1. And now we are interested that when the water level reaches here, this is, let's say, Z2. This is Z2. How much time it will take for water level to change from Z1 to Z2? So this we can calculate by evaluating this integral here. So this is a very general form. This is a very general equation. We can simplify this equation for any specific case. You just need to simplify this equation for any specific case to get the specific formula for that case. This is a very general equation. So how we can get a specific equation for a specific case? Let us consider a case we have a rectangular tank with orifice. Now here we take one case. Now for this rectangular tank, it means that the cross section is constant. Let's say this is length by width of this cross section. So this is the surface area, which is denoted by AS. If you look to the top, this is the tank, the water tank. Now you are interested that how much time it takes for water level to drop from Z1 to Z2. Or let's say this can be an example of a swimming pool. We are interested that how much time the water level will take to drop from one level to another level, or even you want to completely empty the swimming pool, how much time it will take. This we can calculate. So in this case, now what is happening that this AS for a rectangular tank cross section remains the same. You can see throughout now the cross section is same. So what we can do is that AS is equal to constant. In the previous case, AS was a function of Z, because you can see the surface area, it changes with respect to this Z. But now in this case, AS is now constant. Now we have discharge at the orifice, which is now in this case at the bottom of this tank here. So for that, the equation is this: Q naught is equal to CD A into under root 2G Z, where A is the cross-sectional area of the orifice. Now here we are not discussing that this is circular orifice or triangular orifice or rectangular orifice or square orifice, whatever. But we have the cross-sectional area is A, Q naught. Now we have this general equation that we developed in the previous slide. For this specific case, we need to simplify this to get a specific formula that will be applicable for this case. So what we do is that in this case, now AS into dz divided by y, it is 0. Let us say that the inflow discharge is 0. As we already stated that inflow discharge will be either 0 or it will be a constant value. So now instead of Q naught, this Q naught here, this Q naught, we just write down the formula here. So now in this case, if I want to evaluate the integral, so I can just write down the constant outside, because you can see here minus CdA into under root 2g. This is constant, AS is also constant. So that's why this term, this is constant. And you already know that anything constant can be written outside the integral sign. And we just have this z1 by 2. When it goes up, z minus 1 by 2 into dz. Now just evaluate this integral. When you evaluate this integral and take care of this negative sign, then we get t is equal to 2as divided by cdA under root 2g into square root of z1 minus z2. So this is now the specific equation now for this case to calculate the time for water level to drop from z1 to z2. For example, if we want to completely empty the tank, then in that case what will happen? Z2 should be equal to 0. For complete emptying the tank, clear? For complete empty, Z2 should be 0. And then this will be the formula to calculate the time for complete empty. So this is one case I considered. You can now consider any number of cases where you are interested to calculate the time for water level to change from one level to another level. All you have to do is to evaluate this integral. This is a very general formula. Just you consider different cases. Now you have a triangular tank, you have a spherical tank, you have whatever shape you consider, reservoir, you want to drain by a weir, etc. So all you can calculate the time by simplifying this general equation. This is now the general equation that you need to simplify for any case to get the specific formula for that case. So this is unsteady flow problem because discharge is changing with respect to time. So now let us take one or two problems to understand that how we can apply these concepts to solve the unsteady flow problems. So this is problem from our textbook. Now in this case, this problem refers to problem 12.1. What is problem 12.1? Part A of the question is that outflow from a reservoir with vertical sides is over a spillway, Q is equal to CWL H3 by 2. This is discharge over a spillway. Initially there is steady inflow so that the height of water surface above the spillway is Z1. If the inflow is suddenly cut off, prove that the time required for water level to fall from Z1 to Z2 is given by this equation. This is now the equation for time for water level to drop from one level to another level for a reservoir, for a dam. So you need to derive this equation. How we can do it? Same. You just need to simplify this equation. You will get that specific equation for reservoir with a spillway. What is part B of the question? That how long will it take theoretically for outflow to stop, to cease completely? This is part B. How much time it will take for water level to come to such level that the outflow is stopped? And part C of the question is given here. Given the crust of the overflow spillway, the length is 30 meters, the value of CW, coefficient of wear, that is 1.91, and the surface area of water, that is 65,000 square meter, with no inflow, QI is 0. No inflow means that QI, that is equal to 0. Find the time required for water level to fall from 900 millimeter to 300 millimeter. How much time it will take for water level to drop from 900 millimeter to 300 millimeter. So now we go for part A. We have to prove this formula. So again, we know that QI is 0 and Q naught for a wear, that is given by this formula. CWL into Z3 by 2. And what we do is that this formula you have to write down here, this formula. So now in this formula, Qi is 0. So this is how we write down A S dz divided by 0. This is actually 0 minus CWLZ 3 by 2. Now just evaluate this integral. So you will get this formula here for time, for water level to change from Z1 to Z2. So this is part A of the question. Part B of the question, that how long will it take for outflow to stop? So when outflow to stop, we have Z1 and then the water level, it is dropping to Z2. Clear? This is what this formula says, coming from Z1 to Z2. So when the discharge will be 0, when Z2 is 0, then in that case, the discharge will be 0. You are coming from a level to a 0 level where the discharge is 0. So now when you put 0 here, Z2 is equal to 0 here, 1 by 0, what we get? When Z approaches 0, then T approaches infinity. So theoretically, the outflow would never stop. This is what we get the solution, answer. It means that the water over the spillway, it will stop in infinite time. But practically, this is not the case. Practically, if the water level goes below the spillway level, water will stop. So theoretically, we get unrealistic answer. This is unrealistic answer. So it means that something is wrong with our theory that we applied and we calculated this equation. It means that this equation that we derived is based on some assumptions. So that's why we come up with this unrealistic answer. So what could be the possible factors that we get this unrealistic solution? So factors which make this theoretical answer unrealistic include surface tension, surface ripples, evaporation, leakage, seepage losses. So we already know that from a reservoir, there can be evaporation from the water surface. Similarly, there can be water seepage down into the soil. So you see, these factors we did not consider while calculating the equation for the time. So these can be responsible why we get the time as infinity. Part C of the question says that how much time it will take for water level to drop from 900 millimeter to 300 millimeter. So it is easy. We have just this equation that we developed. So from 900 to 300 millimeter, everything is given 0.3 and this is 0.9. Keep the units consistent. So 0.9 and 0.3, and the time that we get will be 1751 seconds, or divide by 60, 29.2 minutes. So this much time it will take for water level to change from 900 millimeter to 300 millimeter. Next, we consider another problem. So in this case, what we have is that 25 millimeter diameter smooth brass pipe. This is the diameter of pipe here. This is the pipe. So its diameter is 25 millimeter. It is 300 meter long. This is total length is 300 meter from here to here. This is 300 meter long. It drains a 1.2 meter diameter cylindrical tank. So it means that the diameter of this tank is 1.2 meter. Now it drains oil. This is oil, not water. It contains oil, and the density and viscosity values are given by this. Now the pipe discharges at elevation 30 meter. It means that at this point here, the elevation is 30 meter. This is 30 meter. Now the question is that find the time required for the oil level to drop from elevation 30 to elevation 32.5 meter. Now the question is that here the elevation is 36 meter. And here the elevation is 32 meter. 32.5 meter. Now how much time it will take? That we need to calculate. So to do that, what we have is that we want to check if the flow is laminar. For that, we will calculate the maximum velocity, and from maximum velocity, the diameter, rho, mu, they are given. We can calculate the Reynolds number, and then Reynolds number can tell us the flow is laminar or it is turbulent. Now elevation in the tank is 36 meter. Because for this 36 meter, we will be maximum. Any level lower than this, velocity will decrease. So that's why at 36 meter, the velocity will be maximum. So now we consider this equation. This is Z 36 meter. minus the major head loss will be equal to this 30 meter here. We ignore other terms, clear? Because we have oil which is flowing and consider laminar flow, so the velocities other than this major head loss, because length of the pipe is 300 meter, which is significant. We ignore other terms. What we left, 36 minus the head losses must be equal to 30 meter. Let's say you are coming from a 36 meter potential to a potential of 30 meter. This will come at the cost of this energy. So 6 is equal to FL by D V square by 2G. Now in this case, what is F? Velocity is unknown. F we can eliminate, because if we assume laminar flow, then we already know that F is equal to 64 by R. This is what we studied. And Reynolds number is rho Vd by mu. Now what we do is that we put this value here, and then this F we put here. When you simplify, then you will get this. You see, in this case, everything is known except V. This V, it cancel out this square. So that's why we are only left with V. And all other terms, diameter, viscosity, density, length, diameter, here, this is 2D, everything is known. So you plug in the value. So 6 is now equal to 49.4 times V, or V will be equal to 6 divided by 49.4. So the maximum velocity, that is now equal to 0.1213 meter per second. Why it is the maximum velocity? Look here. This 6 is 36 minus 30. 30 is fixed. If I go below, this 36 will decrease. Let's say I come to 32.5. So then 32.5 minus 30, just 2.5, divided by 49.4, you will get a small velocity. So that's why for 36, what we have this as the maximum velocity. Now that we know the velocity, you can put here and calculate the Reynolds number to check if the flow is laminar always or not. So what we do is you put in the Reynolds number. Now the Reynolds number for maximum velocity is 96. Since it is less than 2000, so flow is always laminar. Why? Because for any level less than this, the velocity will be less than 0.12. And then in that case, the Reynolds number will be less than 96, but it can never be more than 96. So it means that the flow is always laminar flow. So in general, what we can do is that elevation minus 30 is equal to 49.4 times V. What we write down here, this is fixed. 30 is fixed. 36 can decrease. So 36 minus 36 is equal to 49.4 V. If you want to generally write down, it means that any elevation minus 30, because 30 is fixed, will be equal to this. So accordingly, you will get the value for the velocity. So it means that velocity is equal to elevation minus 30 divided by 49.4 equal to, let's say this we denote by H. So V is equal to H by 49.4. Now Q is equal to AV, pi by 4 into D square, keep the units consistent. V is now H by 49.4. So we get this equation. Now we have this as the volume, Q into dt, the volume. Similarly, A into dH, this is also a volume. AS into dz, remember, Qi is 0. Why minus? Because Qi is 0. So in this case, also the depth is decreasing with time, so the negative sign comes. So now from here, dt, this will be equal to Q by A minus AH dH divided by Q. So now this 0.6, now this is for the tank, 1.2 diameter, so radius is 0.6 meter. Now this will be equal to this expression for dt. Now you want to calculate the time, just integrate this equation here. This is constant, write down outside the integral sign, and we are left with dH by h. So dx by x, integral dx by x, that is log of x. So here dH by h, log of h. And how this limit comes? From 6 to 2.5. Why? Because here it is 36 meter. This is 30 meter here. And this is 32.5 meter. So actually we are coming from 6 to 2.5 meter. So that's why 6 to 2.5 meter, you just evaluate this integral and you will get the answer. Time is equal to 27.7 hours. So it means that it will take 27.7 hours for water level, this oil level, to drop from 36 meter to 32.5 meter. Why it takes so much time? Because the flow is laminar, very, very small velocities. Clear? Next we take another problem.
सर हम इस चैप्टर में अनस्टडी फ्लो डिस्कस कर रहे हैं, तो ये तो लैमिनार तो अनस्टडी नहीं होता है सर.
The problem is that laminar, if it is not steady, This is a separate concept. This is a separate concept. The thing is that when the flow is laminar, is it unsteady or steady? We are discussing, that's why in the beginning I told you, don't try to mix things. Laminar and turbulent is a separate concept. Laminar flow and turbulent flow, if you know the definitions, we studied so much about it, that is a separate concept. Similarly, for fluid, they can be compressible, they can be incompressible. Similarly, for flow can be uniform flow, it can be non-uniform flow. Similarly, the flow can be steady flow, the flow can be unsteady flow. We can have a steady uniform flow. We can have a steady non-uniform flow. We can have a steady laminar flow, can be a steady turbulent flow. Don't try to mix things that because laminar flow, we consider that the velocity profile is not changing in the x direction, it is a steady flow. Clear? So that's why in the beginning I told you that these are different concepts. Don't try to combine them. You already studied them in fluid mechanics 1. You studied about compressible, incompressible fluid. That is related to the density. If the density is constant, we say the fluid is incompressible. If the density is variable, the fluid is compressible. Then you cannot say that if the flow is steady, it should be compressible or it should be incompressible. So that's why in the beginning I clarified this concept that don't try to mix things. It doesn't mean that if a flow is steady, the flow will always be laminar or it will always be turbulent. I hope your question is clear.
तो सर इस प्रॉब्लम में हमने क्यों कहा है कि ये फ्लो लेमिनर होना चाहिए सर?
तो आपने ये जो इक्वेशन है किधर से निकाली है? ये जो आपके पास इक्वेशन आई है ये किधर से निकाली है?
ठीक है सर।
ये फिर आप किधर से निकालेंगे इक्वेशन है? आप ये तो नहीं कह सकते कि बस एक फार्मूला है मेरे पास और ना इसी एक फार्मूले से हम सब कुछ निकालेंगे और हर किस्म के प्रॉब्लम सॉल्व करेंगे। ऐसा तो नहीं हो सकता है। ये तो देखें अभी आपके पास क्या है कि ये इक्वेशन है हमारे पास, तो इस इक्वेशन में आपके पास हमेशा हम क्यू आई 0 लेंगे या कांस्टेंट लेंगे, तो क्यों लेंगे? ऑलरेडी मैंने बता दिया कि दिस क्यू आई कैन बी वेरिएबल। जब ये वेरिएबल होगा आप देखेंगे कि इस इक्वेशन को जब आप इवैल्यूएट करेंगे यू विल गेट कॉम्प्लेक्स इक्वेशंस बिकॉज यू आल्सो कंसीडर क्यू आई को हमने 0 किया, यू सी द इक्वेशन बिकम सिंप्लीफाइड। आप अभी क्यू आई को वेरिएबल ले लें, द सिचुएशन विल बी टोटली डिफरेंट। दिस वेरीज फ्रॉम केस टू केस। So you have to see the nature of the problem, that is the flow steady or unsteady? For the given case, is the flow uniform or non-uniform? For the given case, the fluid is compressible or incompressible? For the given case, the flow is laminar or turbulent? All you have to look from every prospect when we solve the problems. I hope it is now clear.
Yes sir, clear.
Okay, so let me quickly take this problem before I take a break. We need to cover more material. Now we have a variable tank now. In this case, now the discharge is occurring through an orifice here. This is the orifice at the bottom of this tank. So now in this case, we have a cone-shaped tank now. Now the AS is variable. Now it is not constant. You will see that it is now variable. We just consider a simple case here. So AS you can calculate. If it is circular, pi by 4d square, very easy. Now it is variable. So now you will see the problem becomes complex. Whatever, we have to learn how to solve them. So now the question is that we have this cone-shaped tank in the form of frustum of a cone. This is the area of the orifice here at the bottom, and the coefficient of discharge coefficient is given 0.60, and the diameter D1 is 12 meter. This is 12 meter. This is 12 meter. And this diameter D2 is given, it is 5.6 meter. And Z0 is given 10.4 meter. This is given as 10.4 meter. Now it says that how much time it will take for water level to drop from section 1 to section 2. How much time it will take? What is given is that the tank diameter, that is, let's say whatever, small d or capital D, their diameter is equal to k times y, where k is a constant. It means that the diameter is changing with respect to y. It is not constant. This is given in the question. So accordingly you will work. And y is equal to z plus h2. This is now given in the question. So now we have to solve the problem. For these given conditions we have to put. Then you will say that why it is given k times y instead of ka is not written. So this is not a question. The question is you are given a situation and then accordingly you consider the situations and try to solve the problem. This is what we learn through these examples and practice of fluid mechanics or whatever mechanics you study. Clear? So now in this case, because the diameter is variable, so we have to calculate AS. What is the big problem here? The big problem is AS. In the equation now, AS is variable, QI is 0, AS is orifice. You have a simple formula. So now what is the biggest challenge in this question? How we calculate AS, which is now variable? If it was constant, very easy problem. So now how to calculate this? There are actually two approaches. I will teach you two approaches, how you can follow, up to you, which one you easily understand and easy for you, convenient for you, you can follow and solve the problem. So the first approach is that you can see that we can compare these similarity triangles that can form here. So H2 divided by Z0, this H2 divided by Z0, this is equal to D2 minus 0, but 0 not written, D2 divided by D1 minus D2. It says that this ratio is same as this ratio. This is how it is written. Left hand side is equal to the right hand side. So from here we can simplify. H2 is equal to D2 into Z0 divided by D1 minus D2. Now everything is known. Just plug in the value. So H2 is now 9.1 meter. And now we are given that this Y is equal to Z plus H2. What is Z? Z is essentially this distance. Y minus H2 will be your Z. And we have to express the area in terms of Z. Why? Because in the equation, what we have, in this equation, what we have, we talk about this dz. So if you want to evaluate the integral, you have to express the variables in terms of z. That's why we are doing here. We have to now express this area in terms of z now. So now your H2 is 9.1 meter. So now Y is Z plus H2. So Z is variable. So 9 plus 9.1. Now we are given that D is equal to K times Y. So D has to be expressed in terms of this Y here. But Y is now equal to Z plus 9.1. So what we can write down is that K is equal to D by Y. This is given by this values. K is a constant, 0.615. This is the change which is occurring. What is the change occurring in the diameter in 10.4? In 10.4, what is the change occurring? From 5.6 to 12. So what is the change occurring in 10.4? 12 minus 5.6. So it means that this equation is now equal to what? This is equal to D into 0.615 times Y. So now you change the Y, you change the diameter, and you can see here. But because we have to express this in terms of Z, not Y, so that's why in AS pi by 4 D square, D will be equal to 0.615 times Y, but now Y we have to replace by Z. So what you will do is that AS is equal to 0.297 into Z plus 9.1 whole square. So now your AS is expressed in terms of Z. So now DZ and Z here, we will be able to evaluate the integral to calculate the time for water level to come from 1 to 2. Now the question is easy. QI is 0 and Q naught, it is given by this simple formula for the orifice. Z is variable. So now you just put Q naught is a function of Z, and now we say AS. You put AS here and you put Q naught as here. QI is 0 and the water level drops. This total is 10.4 meter. This is 10.4 meter. This is 12 meter. And this is how much? 5.6 meter. So now you can see the integral is now complex. So you have to evaluate the water level comes from 10.4 to 0 here. 10.4 to 0. Just evaluate this integral and it will take 605 seconds for water level to come from 1 to 2. Divide by 60, you can calculate in minutes, whatever hours you are interested. So this was one approach to calculate the AS. If you are not convenient, there is another approach. I teach you another approach that we express directly the diameter as a function of Z. So how we do it? That here the diameter is 5.6 meter. So this is 5.6 and then it increases to maximum 12 meter. So we say that let us assume this is Z. Because I'm interested, I can calculate the diameter at any intermediate point. So in 10.4 meter, in this 10.4 meter, how much the change is occurring? 12 minus 5.6. This is the change occurring. When you simplify, this is equal to 5.6 plus 0.615 times Z. Okay. If you want to check that this equation is correct or not. So let's say I want to calculate what is the diameter here. Let us calculate this value. So in here, when the diameter is 12 meter, what is Z? Z is 10.4. You put this as 10.4. When you put this 10.4, this cancel out with this 10.4. And this 5.6 cancel out minus 5.6. What we are left? Diameter is 12 meter. And this is 12 meter. So now we can express the diameter in this form. Now we have the area, which is pi by 4 d square. And now we get pi by 4 into 5.6 plus 0.615 z whole square. And if you simplify, we get A is equal to 0.297 into 9.1 plus z whole square. And you can see that this equation, this is essentially the same as we get this equation. You can see here, this is same as this. So any approach you want to follow, convenient to you, you can follow and you can get this answer.